Okay, so okay, okay, so I think we have to start. Well, in the last technical session, we talk about some basic machine learning algorithms like what is classification, what is regression, and we also introduced the support vector machine, which is actually I think. One of the simplest classification algorithm. So today, in the technical session, I want to introduce a very interesting topic. I believe most of you will use deep neural network to solve your the problem in your project, right? So today I will introduce some basic theory and computations about deep neural networks. So okay, so what is neural networks? So this picture actually illustrates the neural network in a very good way. You can treat the neural network as actually a Lego. So you can build the neural network in any way you want with the basic Lego blocks, which are linear classifiers. So basically from this figure, you can see the neural network is a stack of linear classifiers. And of course, we will add some nonlinear functions between them. So, as I mentioned, the neural network is a stack of linear classifiers. That means we need to know what is a linear classifier. Actually, I think I have introduced a linear classifier in our first lecture, which is about the classification. So, but now let's have some recap. So before introducing the linear classifiers, we need to know what is the task of classification. So take image classification task as an example. So given an image, you need to learn a model to classify it into one known category. For example, the famous CIFAR-10 dataset has 50,000 training images and 10,000 testing images. So each image in the dataset can be categorized into one of the 10 classes. The size of the image is about 32 by 32 with RGB3 channels. So totally you have 50,000 training images, and each image size is 32 by 32 by 3. 3 is the channel size, and you have 10,000 test images, and you will have totally 10 classes. This is a very famous, image classification dataset called CIFAR-10. We also have the CIFAR-100, that means you have 100 classes. So in CIFAR-10, you need to classify these images into different classes. For example, sheep, horse, frog. So most of them are animals. So that's a kind of very classical image computer vision problem, which is called image classification. So the most common way we use to classify the image or any other data formats is a parametric way, which means we need to learn some parameters to classify the data, right? So take this image as an example. We want to learn a parameter matrix W for some function f with the input x. So here the x is the input, so the x is the image actually. So the output of the function are 10 numbers give the class scores. Because we have 10 classes, right, we want to classify this image into one of the 10 classes. So that means output, ideally, we have 10 numbers, right? So each number gives me a score, like whether this image belongs to that class, right? Normally, we can use a parametric approach to solve this problem. Parametric approach means that we want to learn some parameters during the training and use that parameters during the testing. So here W is the parameters that we want to learn, and X is the input, F is some predefined function. So a linear classifier just means the F is the F, the function F, the prediction function F is a linear classifier, is a linear function. The simplest linear function is W times X, right? So X is input, W is the parameter that we want to learn from our training data. So in this case, X So the size of the X will be 3072 by 1 because it's 32 by 32 by 3. If we stretch this image into a long vector, into a single vector, there will be 3072 total numbers in total. So so that means X is actually, the dimension is 3072. And we know the output is 10. Right, so we want to output 10 numbers. So that means the W, the parameter matrix, the size of the parameter matrix need to be 10 times 3072, right? So because this matrix times this vector, the output will be 10 by 1, right? So this is a mathematical, this is a matrix multiplication. So output is 10, the size is 10, right? So each value is actually give you a score that whether this image belongs to this class or whether this image belongs to that class, right? So this is a classical linear classifier. And sometimes we also add the B, which is called a bias. The size of the bias is also 10 times 1 because here output of the Wx is 10 times 1, so we want to add a bias. So this is the simplest linear function, Wx plus b. I have introduced this one in the previous technical session. So, well, let's take this image as an example, and we assume there are only 4 pixels inside the image. Well, of course, I know this is 32 by 32 by 3. It's 3072, all right? So, but let's just assume in this image we only have 4 pixels, and the pixel value is 56, 231, 24, and 2. We only have 4 pixels, okay? So, and we want to classify it into one of 3 classes, right? So we want to know whether this image is a cat or dog or sheep, right? So we have 3 classes. And so here W is actually, it will be a 3 by 4 matrix. The input data X is a vector with 4 values. The bias B is a vector with a linear function. We have the output with 3 scores, right? So here you can see this 56, 231, 24, 2, it become a vector, right? This vector, we stretch the pixels into columns. And this W is some parameter matrix that we want to learn. And also the bias is something that we want to learn. So in this case, let's assume the learned parameter W is this 3 by 4 matrix, and this is 3 by 1 vector, the bias. So if we W times X plus B, so this one will give us output which has 3 numbers. As we can see, the biggest one is a dog, 437.9, which is a dog score. This is the biggest one. So that means actually, if you use this W and B, the output, the predict of this classifier will tell you this input image is a dog, right? Of course, it's not right. We know it's a cat. So that means we need to adjust this W and B to make it predict as a cat. So this is how we can adjust those parameters. That's why we need a lot of training data to tell our classifier that is cat, that is cat, this is a cat. Then it will adjust this W slightly to make sure in the training data it can predict it as a cat, right? So this is an image example with an image with 4 pixels. So so what's this thing doing? So what is the meaning of the W, right? So we have fx equal to wx plus b. So what's the meaning of W, right? So it's a kind of classifier, right? So here we actually display the trained weights of a linear classifier of 10 classes on the CIFAR 10. Looks like they are just some blurry, colorful images, right? So that's well, we display the W basically, but actually we cannot see clearly. But from these patches, you can observe some characteristics of the object class. For example, sheep, because sheep is always on the sea, so the background is actually like blue and similar as a plane, and this is a car, a bird, So this is a W we have learned. So it's actually learned some features from the images, right? So mathematically, actually, for a linear classifier, we also introduced the one in our previous technical session. So fx equal to wx plus b. So the w is basically a slope of a straight line, and b is intersection, right? So basically, we want to learn a linear classifier to classify the image into different classes, and different w can for example, this is a car classifier. So the red line is a car classifier, right? So if one image, if we have a test image, and the test image is here, then that means it's a car. If it's here, then it's not a car. It might be something else, right? And here, this 3D figure shows is it's high dimensional, right? So of course, it's not only in 2-dimensional. It's it might be higher dimensional. So in 3 dimension, it's like a plane. So the W is like a plane, right? So that's how can we interpret a linear classifier. So basically, the linear classifier learn a classification. A straight line or a plane to divide the space, a feature space, into different parts, and you will give you a testing data, and you can test whether this new data is above the line or lower the line. So that means you can know which class it belongs to. So the basic assumption of the linear classifier is that the data can be divided linearly, right? But in many cases, this is not true. For example, there are 3 cases. In the figure, you cannot simply use straight lines to classify them. Then you will need the nonlinear classifiers, right? So for example, in this case, in the first case, right, the blue class is a number of pixels that's bigger than 0, but odd numbers, and class 2 is a number of pixels that's bigger than 0, but even. Right, so actually, you cannot simply draw a line to divide the space into 2 parts, right? So in this case, it's a nonlinear classification problem. You cannot rely on a linear classifier to do the job, right? So, that's the basic idea of the linear classifier. So after we understand the linear classifier, let's go to the next part, the neural networks, right? So as I mentioned, the neural networks is basically a stack of linear classifiers, but between them we need to add some nonlinear classifiers because the data is not, sometimes the data is not linear separable. So, okay, so we already know that a linear score function looks like this, right? W times x. The bias b is omitted here just for simplicity, right? So this is a classic linear score function. Then a 2-layer neural network can be defined as this, so which is W2 times max between 0 and W1x. So max 0 and this max function is actually a nonlinear function, right? So W1x, this is a linear. Max, nonlinear. W2, another linear. So as you can see, this is the simplest 2-layer neural network. And we have one linear function, one nonlinear function, and another linear function, right? So max here is actually a nonlinear operation. So in this case, except the input x and the output s, as represented in a linear classifier, we actually has one more middle state, which is h over here. So we normally call it as a hidden state. So in this example, the x is a vector with 3072 numbers. After the linear transformation with W1, we get a vector h with 100 numbers. So this is the hidden state. The h is then input to a nonlinear function. Here is simply a max function. Then the output is equal to another linear transformation with a parameter W2. Right? So we have actually W1, W2. This is called a 2-layer neural network. So the input x, first use input x the size is 3072, right? Because our image is 32 by 32 by 3. It's a vector. If we stretch the image into a vector, it will be 3000 dimension. And we first use the linear transformation, W1 times X, and output is 100, will give me a hidden state. And at this place, I run the nonlinear function, which is a max 0 and W1x. So that means if I have 100 numbers, for each number I will run this nonlinear operation, which give me another 100 output. And use that output, I will times the W2, which is another linear function. Then the output is 10. So that means the size of the W2 is actually 100 times 10, so that I can get the output which has the size of 10. Right, so inside the H we have the nonlinear operation. So in this case, actually you can see the neural network is like a linear, nonlinear, then linear. Right, so there's a simplest two-layer neural network. So and also and so on, the three-layer neural network is like this. So we have first W1x, the linear function, then max, nonlinear, W2, another linear, then another max, another nonlinear, then W3, another linear. So it's basically a stack of the linear, nonlinear, linear, and nonlinear. So it will give us a neural network, right? So it's basically that's the basic idea of a neural network. It's basically a combination of the linear functions and nonlinear functions, right? So then in this way you can transform your original data into some other high-dimensional data space, right? But with both linear and nonlinear operations. So, well, that means the implementation of the training a two-layer neural network is super simple. It's just actually, if you write it down in Python, it only needs 20 lines to finish the two-layer neural networks. Okay. Okay, so one question you may want to ask is, why do we call it neural networks? It's just a stack of several linear transformations. So what is the connection between the neural networks and our real biological neurons? So why should we call it as neural networks? It's just it's basically just a combination of a stack of linear functions and nonlinear functions, right? So why should we call it as neural networks? So because neural network is kind of a biological thing, right? So here is a biological neural. So the cell body is at the center. So at the front end, at the front end, impulse is carried toward the cell body, and at the back end, impulse is carried away from the cell body, right? So this is basically a biological neural. So are there any common properties between this one and the neural networks? So the lower part actually shows a neural in the machine learning field. So X is the input, as we mentioned. For example, X can be an image. It can be treated as a signal in the real neural, right? In the real neural, we actually receive some signals, right? For example, you have a human eye, you have an ear, so you already receive different signals, right? So the input is a signal. Then the input will times the weight W, which is the weight matrix we will learn in our machine learning model is actually like the synapse in the real neural system, and the summarized operation is like the cell body in the real neural, which will receive all the information and output through the axon. So this is why actually there is some correspondence between the machine learning based neural networks and the real neural networks, right? So that's why we call it neural networks. So note that we also need an activation function, which is a nonlinear operation, so that we can address very complex nonlinear classification problems. Well, as we mentioned in some feature distribution, we cannot solve that by using the linear function. We need to use a nonlinear operation. And in neural networks, we have the stack of linear and nonlinear operations. And we here the sigmoid activation function is one of the most classical activation functions, the nonlinear functions we use in the neural networks. And the max function between 0 and the value is also one of the simplest nonlinear function we use in the neural networks. Well, so also, although we are trying to match the neural network with the biological neurons, there are still many differences. For example, many different types. The dendroids can perform complex nonlinear computations. Synapses are not a single weight, but a complex nonlinear dynamic systems, right? But in the real neural networks, it's basically a weight matrix, right? And rate code may not be adequate, right? So we still there are some differences between the biological and the machine learning and the machine-based neurons, right? So, okay, we already know that a neural network is a stack of multiple linear classifiers, and it can provide that combination of several linear classifiers. It's actually we can prove that. If we only have a stack of linear functions, right? So think about if you have a neural network, and in that neural network you don't have any nonlinear functions, all linear operations, right? So one linear, second linear, third linear. So no matter how many linear functions you use in that neural network, it's always a linear function, right? So we can prove it mathematically, actually. So basically a combination of several linear classifier is still a linear classifier. So to make the neural network as a nonlinear classifier, we apply the nonlinear activation functions on the neurons, right? So here are some commonly used activation. Here are some commonly used activation functions. In our previous example, we used the ReLU function. So if you still remember our previous two-layer neural networks, right? So we use a max 0x, max 0 between 0 and x, right? So this is plot in the feature space, right? In the 2D space, max 0 and x. This is a typical nonlinear function. And we also have some other kinds of nonlinear function like sigmoid, tangent H, leaky ReLU, max odd, and ELU. So they are all different kinds of nonlinear functions. So basically, ReLU function and the sigmoid function are mostly used in the neural networks. So yeah.
How can we choose a specific activation function when we do some specific classifier work?
Okay, normally there are no big differences of using different linear functions. So it totally depends on your data. So it's different activation functions may have different effect on your data. Sometimes, well, there's no actually a good theory to prove that which activation function is good for which kind of data set. But normally, ReLU function and sigmoid functions are mostly useful activation functions in the convolutional neural networks, right? So one problem of the ReLU function is that, as you can see, if your input value x is smaller than 0, then the output is always 0, right? So that's why sometimes if you find the value is always negative, the ReLU function will be not useful. So in that case, we will use the leaky ReLU. So in the leaky ReLU, even the value is smaller than 0, you still get some value, right? So it really depends on your data. Yeah, but there's some commonly used activation functions. So to summarize a neural network, we can see there are mainly actually 3 types of layers, which are input layer, right? The input X. So in our image classification case, that will be the image, right? And we also have the hidden layers and output layer. The left side is a 2-layer neural net. We normally don't count, well, what we call it 2-layer neural net, right? So normally we don't count the input layer, we only count the actually the hidden layer and the output layer. So then the right case is actually a 3-layer neural net, or sometimes we call it a 2 hidden layer neural net. Right? We only count the hidden how many hidden layers and how many output. Normally we only have 1 output layer, right? So and the depth of the neural network is totally depends on how many hidden layers you have, right? So they are saying that the more deep of your neural network, better performance you can get, right? So that's the number of layers. So this is a typical neural network, and as you can see, actually we also call it as a fully connected neural network, because each neuron is connected to all the neurons at the second layer, right? At the next layer. And again here, if you have 4 neurons and the 4 neurons, you have it's fully connected. So we call it as fully connected layers or fully connected neural networks, right? But later, actually, we will introduce this is not the best option, right? Because in this way, you will have too many parameters. So, okay, summary so far. Basically, we arrange neurons into fully connected layers. The abstraction of a layer has a nice property that it allows us to use efficient vectorized code, like matrix multiplies. Neural networks are not really neuron, actually. So, okay, next I will introduce the most important part, the convolutional neural networks, which has been widely used in the computer vision area, right? So if you want to do the image classification, segmentation, all kinds of things that is related that are related to the image processing, then you will use the convolutional neural networks. So before going to more details, let's see a bit of history at first. The Mach 1 perception machine was actually the first implementation of the perception algorithm. The machine was connected to a camera that used 2120 cadmium sulfide photocells to produce 400 pixel images. So each light here in this image, actually each light is actually a pixel. You can treat it as a pixel of an image, right? So in this machine, it's actually a simple linear classifier, which is if W is basically just a simple WX plus B, right? So in this machine, to just implement this one, it's called Mach 1 perception machine. So in 1960, some people built a physical device that implement an early single-layer artificial neural network. So the Mach 1 perception is just a linear classifier. So they basically they use a motherboard to implement a single linear classifier. But for this one, it's actually a single layer neural network. In this one, it's called Adeline, and actually later a multi-layer network of the Adeline are implemented. It's called the Madeline. So this is some physical device devices of doing the neural networks. So in 1986, the first time the backpropagation became popular. The backpropagation is a way to train the neural networks. Actually, we are still using it today. So the backpropagation is used to calculate the gradient, because, well, I don't want to introduce this one. So if you learn the machine learning tools, or the statistical machine learning last semester, I believe you will learn this. So basically, if we want to train a neural network, if we want to update the parameters, we need to calculate the gradients at first. So to calculate the gradients, because there are so many layers, if we want to calculate the gradient at each layer, it will be very hard. So that means we need to use some thing called chain rule to calculate the gradients. and the backpropagation is a way to calculate is a way of using the chain rule to calculate the gradients. So nowadays we're still using this one. We are still using the backpropagation to calculate the gradients in our neural networks. So this one is very important technique for the deep learning. Actually, without the backpropagation, there will be no success of the deep learning. Okay, then the neural networks in computer vision experienced a long-term silence until 2006. Hinton et al. Actually, use this network to do the face classification, and LeCun et al. Actually use a neural network to do the character recognition, which is the first strong result. So basically, in 2012, they produced the first strong results on the image classification task by using the deep convolutional neural networks. That is the most famous AlexNet, and Hinton et al. Currently is leading researcher in Google. Basically, you can see Hinton is jobs in the deep learning field. He reviews this monster. So actually after 2000, so before the 2012, not a lot of people trusted the neural networks because it's hard to train, it's too deep. But after 2012, actually people find the way to train the neural networks better by using the GPU and make it work better on the image classification. This is the first strong results actually of using the deep neural networks just in 2012, nearly 10 years ago, but in a short time, and it's totally different. So after that point, convolutional neural networks are everywhere, from the image classification to the image retrieval problem, and from the object detection to the segmentation problem. So detection problem is like we want to detect the object inside the image, right? We want to give a bounding box of the image. And the image classification problem is like here. We only want to know the label of the image. For example, for example, there is a dog, mushrooms, car. So we just want to know the class label of the object that appeared in the image. And for the image retrieval problem, it's like here the first column is input image, and we want to retrieve similar images from the database, right? For example, in the Google image, if you upload an image and you want to search the similest image from the most similar image from the Google, basically that's the image retrieval, and they are using a deep learning method, the convolutional neural network, to solve this problem. And we also do the detection. Yeah, so for the detection, I mentioned it's a bounding box issue, right? So we want to detect the bounding box, but not only in the bounding box. We also want to know the label. For example, there are two dogs. That's a bounding box, red one, blue one. And we also have the image segmentation problem, which is slightly harder than the object detection. So in the object detection, we only want to know the bounding box, right? So, but in the segmentation, we need to know the pixels of the object, right? So this is a pixel labeling problem. So that's a segmentation. In the segmentation, we also use the image class. We also use the convolutional neural networks. So, okay, so self-driving is also use the techniques of the CNN and the convolutional neural networks, right? So the Tesla, so the self-driving car, right? So they need to recognize the pedestrians, cars, and the traffic lights. They need to use the CNN to do this kind of things. And on the right side is a GPU, right? So without the GPU, we cannot compute the gradients. We can't do the neural networks, right? So well, basically, NVIDIA, they invented the GPU, and it's very expensive. So, for example, in Adelaide University, we got hundreds of V100, and each V100 was, I think, is how much? $20,000. So it's very expensive. And the convolutional neural networks are used on the video processing and understanding as well. Basically, videos are quite similar to the images, right? So in the videos, it's basically you have different you have multiple frames, and each frame is actually a simple image, right? Okay, and motion detection and tracking. So in your project, I noticed some of you are doing the key point detection. So convolutional neural network is definitely one of the options, right? So you can use the convolutional neural networks to detect the key points, the joints of the human. And we also have the reinforced learning. So in the reinforced learning, you can use the reinforced learning algorithm to train an agent to play games. So like StarCraft, so OpenAI and Google Research have done a lot of works in this field. For example, Google Research, DeepMind, basically DeepMind, train the reinforced learning algorithm to play the Go, right? The AlphaGo. AlphaGo is basically a reinforced learning algorithm, right? So you can train a reinforced learning algorithm to play games. But before to run the reinforced learning, you still, if you are playing video games, right? In the video game, you still need to recognize the image information from the video input, right? So that means you need to use the convolutional neural network to do this kind of things. Okay, so people are using the convolutional neural network to recognize everything from recognizing the largest star class to the smallest traffic signs, right? Yeah, so we can use convolutional networks to recognize the black hole, the stars, and we also can train a neural network to recognize the traffic signs, right? And we also can combine the natural language processing and the computer vision, right? So this is actually the topic I'm working on. It's called as image captioning. So in the image captioning, give you an image, and we want to automatically generate a language description. For example, here the input is the image, and the caption we want to generate is a white teddy bear sitting in the grass, right? So it's very accurate. So this is some work that we can combine the computer vision and natural language processing. Another important topic in the image, in the vision and the language, yeah, we call this area as vision and language. So some other important topic in the vision and the language is called the visual question answering. So in the visual question answering, give you an image and a question. We want to generate an answer. For example, we can ask the second image like what's the game the man is playing? So the answer is baseball, right? So you can ask and what's the color of the shirt the man is wearing? So the answer is blue, right? So we can ask any question to the image, and the visual question answering model can answer that question. So it's also rely on the computer vision. So convolutional neural networks are also used in the art area. These paintings are actually drawn from the neural networks, right? So the left side. So I know that some people actually are trying to sell those neural network generated images, and the price is very high. Actually, it's very expensive. But all these images are generated by neural network. It's actually quite amazing. So, and we also can do the style transfer, right? So here is the input image, and you have a Van Gogh style, and it can generate the style of that with this style, but given this contents, right? So it's called style transfer. So basically, convolutional neural networks can be used to generate artworks. That's very interesting. Okay, so So now let's talk. So we just talk about why. Well, we just talk about how people use the how the computer vision people use the convolutional networks, and that's why the convolutional network is very important. Next, let's talk about why do we need the convolutional networks? Right? We introduced the neural networks. We introduced the linear classifier, but why do we need the convolutional neural network, right? So in CIFAR 10, images are only of size like 32 by 32 by 3, right? Because we have 32 wide, 32 high, and 3 color channels. So a single fully connected neural is in a first hidden layer of a regular neural network. Would have like a 32 by 32 by 3, which is equal to 3072 weights, right? If 3072 weights is just for one class, right? Think about if you have 10 classes, right? If you want to classify the image into one of 10 classes, the weight matrix will be 10 times 3072, right? So that means it will be 30,000 parameters in this weight matrix W, right? So this amount still seems manageable, but clearly this fully connected structure doesn't scale to larger images. For example, an image of more image with higher resolution, like 200 times 200 times 3, would lead to a neural that have 200 times 200 times 3, which is equal to 120,000, right? We would almost certainly want to have several such neurons, so the parameters would add up quickly. And we also want to classify the image into different like 10, or even, for example, in the ImageNet we have more than 1,000 classes. So if we want to train a fully connected network to classify the image into 1,000 classes, and if we want to have a deep layer, we want to have deep layers, for example 10 layers. For example, the AlexNet has 8 layers, right? And if we want to train the ResNet is 152 layers. So more than 152 layers. If they are all fully connected layers, that's nearly impossible, because you will have billions of parameters, right? It's really hard to train that one. And this also means the fully connectivity is wasteful, and the huge number of parameters would quickly lead to overfitting, right? So convolutional neural networks take advantage of the fact that the input consists of images, and they constrain the architecture in a more sensible way. In particular, unlike a regular neural network, the layers of a convolutional neural network have neurons arranged in 3 dimensions: width, height, depth. For example, the input images in CIFAR 10 are an input volume of activations, and the volume has dimension of 32 by 32 by 3. So the neurons in a layer will only be connected to a small region of a layer before it, instead of all of the neurons in a fully connected manner, right? So basically, the neural net, by using neural network, we only focus on small patch of the image. We don't need to connect. We don't need to use the fully connected layers, right? So a simple convolutional neural network is basically a sequence of layers, and every layer of a convolutional neural network transforms one volume of activations to another through a differentiable function. We use 3 main types of layers to build convolutional neural network architecture. Basically, we call it convolutional layer, pooling layer, and fully connected layer. We will stack these layers to form a full convolutional neural network architecture. So in the next part, I will introduce the convolutional layer at first. So the convolutional layer is a core building block of a convolutional neural network that does most of the computation heavy heavy lifting, right? So assume our input is still an image with 32 by 32 by 3, and we can actually use a convolutional layer to preserve the spatial structure. And now in the fully connected layers, if you still remember, we have to connect each neural with neurals at the second layer, right? But in the convolutional networks, it's quite different. We will first define a filter. So, for example, in this case, the filter size is just a 5 by 5 by 3. Right? So that means the number of parameters just a 5 by 5 by 3. Then in the convolutional networks, we can convolve the filter with the image. That means we slide over the image spatially, computing dot product between this filter and the patches on this image, right? So that's a convolutional filter. So basically, every filter is small spatially, but extends through the full depth of the input volume. For example, a typical filter on first layer of a convolution neural network might have size 5 by 5 by 3. So during the forward pass, we basically slide, more precisely convolve. Basically we convolve this filter on this image, right? So that's why we call it as convolutional neural networks, right? So we basically convolve or slide each filter across the width and height of the input volume and compute dot products between the entries of the filter and the input at any position. For example, suppose that the input volume has the size of 32 by 32 by 3. It's a typical RGB CFR10 image. And if the repetitive field, or we call it the filter size, is 5 by 5, then each neural in the convolutional layer will have weight to a 5 by 5 3 region in the input volume for a total which is just 5 by 5 by 3 equal to 75 weights. And of course, we also need to add a bias, right? If you still remember, we also have a one bias parameter. And notice that extent of the connectivity along the depth axis must be 3, since this is the depth of the input volume, right? So the filter size must be 5. So this two value, 5 and 5, this can be changed, right? So it can be 3 by 3 or 7 by 7, right? Depends on your design. But the 3 must be same as the input one because you have RGB channels, right? Okay, I think we can have a break, then we can come back 10 past 2. Okay, then I will continue to introduce the convolutional neural networks.
咱们今年申的这些学生，他都拿了论文来，对，有几篇论文是？
对，他们都是有论文的。
成绩上有要求吗？
成绩看你申请学校的奖学金，还是申请我们就是老师自己的奖学金。
哦。
这怎么回事？
是要重启这个系统。
奇怪，刚才还好。 试一下。哎，这个很奇怪啊。这也没有开关，只有这个，但是我已经重启过了，没有反应。这怎么搞的？还是这玩意儿搞坏了吗？
这要按吗？
这个好像这边也没有电话，是应该往上打。
上面的线都连着的。
对啊。太奇怪了。
之前我们在别的教室上课也碰到这种情况，就是按正常设置走之后，他就没办法把 PPT 推上去。
不是，这个是直接那什么啊？直接这个玩意儿好像是挂了。
顿移不行是吗？
对呀、这边应该有一个那个联系电话的，那个 IT 的，这边也没有。这边也没有。啊，我搞不定了，不知道。只能回去那什么。好像网也断了。那个。太诡异了。你们光是，哎，好像有。
这个可以，是不是他得把这个插回去才行？
不至于吧？哎，好了。但是录像好像没有了。
我看一下这个。
哎，好像我刚刚又 go back。Waiting for live stream。这怎么搞呢？只能在
New connection。
New Class。 我们这个是哪个教室来着
208。
08，这是叫 EM 是吧？
不是 EM，是那个尼帕尔。我这边可以看到这个。
对，我也可以看到，但是它好像，但是这边没有开始直播，所以就很208是吗？
对。
它这边为什么没有呢？
要不再重新开始一个。
我这边还设置不了这个东西，就是这个
录音的。
对对，这样的话我这边连 recording 都没有。
是得从学校那边设置。
对，它是学校那边管的，我这边做不了任何改动。
那要登进这个电脑吗？
和那个没关系，是它这个系统的问题。它这显示的这个 Echo 360 No Recording 这个玩意儿。我再重启一下试一下吧。重启一下看看。实在不行也没办法了。
这里有一个电话，你看可不可以打开？
好，这个
报修的是吗？
看一下吧。还是没有。关键是这个，我连录像都没有的话，就比较难搞。
对。
没办法了。
他如果要学校后台的话，咱们要不打个电话给那个 IT support，然后它
看一下 IT support。
8313。
这个是。看现在12点，我估计也来不及了，估计他们也那什么，这个只能打内线，好像是。不行，这个只能打内线，这个电话不能打。看看它的内线是多少。
要不我打个电话问一下。
来，这个是33000，应该可以。
喂，你好。哎，hello。哎，你好，你是哪位？哦，没事没事，不好意思，打错了啊。打错了，不好意思。Shit, didn't answer the phone. Normally there's some number that you can call to, you know. Yeah. Number call.
不接呀，只能后面上传一个 video，可能会把去年录的 video 上传了。
其实很多课都有去年录的 reading。
是吗？
对，就因为去年都是网课。
没有，其实每年都录的，就每年就之前没有疫情的时候，我们上课也会这样，也要录的。
感觉学校是不是削减了很多这种支持人员的精力？
是啊，搞得好麻烦。
学校为什么这么缺钱
呢？因为没有学生了。
南澳大学最近就挺有钱的。南澳大学今年好像收了很多国际学生。就是那种国际研究的学生，读博士、硕士什么的。
啊，还有没有接？我们今天是讲不成了。我稍后把那个 video upload 上去吧，我这边应该有去年的 video。
可以。学校是裁了很多这种就是做辅助的人员。
我还在 in the queue number 5。
number 5，那就。那老师都没有办法自己打开这个 recording， 还得他在后台打开才行。
是啊。估计也得10分钟，那就回去上传了就算了。
可以。
也许不光我们这边，他如果这么多人打电话的话，很有可能那什么。
都是断的吧？因为我看这2天有那个消息，有通知说会发生 technical issue， 就是那个学校 IT support 发了一个可能会网络不稳定的那个。
对，也有可能刚才是那个 networking 断掉了，因为刚才我确实是连不上网了。OK， 那我们今天就先这样吧，不好意思了。那个我后面把那个 video 上传了。
现在主要是学生太少了。
如果都是 in person 的，以前我们也出现过这种情况，但大家都是 in person 的，所以现在主要是反正都是混合的，就 in person 的他也不愿意来了，然后就全部都是 online 啊什么的，搞得上课的人也很少。
是，
除非就是说你搞成那种就是直接在这边考试啊，或者是就像我们一样那种你 presentation 你不得不来，对吧？没办法。
presentation 现在也很少人在这里。
对，大家，我下次 presentation 就变成那个就变成那个什么的了，online 的。行吧，这个估计也搞不好了。
行。
去这个 online 然后。